Is being recorded.
Okay, welcome everyone to this week's OMR Architecture Meeting. I hope everyone is doing well and that they're keeping safe. This week we have a number of topics to go through. So first off is a project that some students at the University of Alberta are working on for tree interpretation, and I will turn it over to Daniel and Alex.
Thanks, Daryl. So hey everyone, we're going to present our work on the OMR tree interpreter. It'll be Alex, Lee, and myself, and we got mentorship from Andrew Craig and Daryl Meyer. And yeah, as Daryl said, it was facilitated by Canos with collaboration from the University of Alberta.
So the goal of the project is build a abstract interpreter that interprets the IL tree during optimization, which could be used by a more sophisticated inliner.
Sorry to interrupt. Your screen isn't being shared anymore.
My screen isn't being shared anymore?
I don't believe so. I don't see it.
Oh, strange. Maybe it's in like the presentation mode, so I'll just leave it like this.
Okay, so I'll just restart. So the goal of the project was to build an abstract interpreter that interprets the IL tree during optimization that could be used by an improved inliner optimization. The abstract interpreter would return a value propagation constraint, which would help the inliner decide what to optimize. So in our project, we built the foundation, the basic infrastructure of an interpreter that returns a concrete value instead of the VP constraint, which could be called from the JitBuilder to interpret the IL tree instead of compiling it. And the way we implemented it is by setting it up as an optimization. An interpreter optimization strategy was created, which only includes the IL tree interpreter optimization. This could be changed to follow its own code path in the future instead of treating it just as an optimization. The interpreter can be invoked by calling interpret method in OMR method builder class. The method starts the compilation process with no opt optimization warmness, which points it to the interpreter without any other optimizations. The actual interpretation starts when the method is already resolved and the IL tree is generated by the compiler itself. The result of the interpreter is stored in the compilation object, the OMR compilation class. So we created a field and a getter and a setter in that class. When the interpreter is finished, the result is stored in that object, and the compiler is interrupted with a compilation interrupted exception. The interpreter then returns the result to the caller. I'll just talk about the interpretation process a little bit before Daniel walks us through an example. So the interpreter walks through a basic block. So one by one, each treetop gets processed, and each process gets processed using a post-order traversal of the tree. Each node is stored in a node value map, which maps different nodes to their values. When a node is processed, if it's newly encountered node, it is evaluated, and the result is stored in the map. If it is a common node or a duplicating node that was previously already evaluated, the result is retrieved from the map to prevent multiple evaluation of the same node. Each value is represented by a struct with a union for the data and a num for the data type. The data union is basically a union of different basic data types. This value could be replaced by VP constraint in the future to build an abstract interpreter. And the loads and stores are implemented using a separate symbol table from the OMR symbol table. We try to use a separate symbol table to decouple it from the actual compiler to keep the unnecessary overhead low. And next, Daniel will walk you guys through an example.
Yeah, so this is just a basic program that showcases some of the features we implemented. So we're just storing the value 7 into a variable A, the 2 into a variable B, and then just adding these two together and returning them. So this is an example of what the log looks like from running our example. So that's how the treetops look. And so first we go into the first node and we initialize a constant 7. And we put that into the node value map. Then we move on to storing constant 7 into A for node 2. But we see that it's already in the node value map, so we retrieve it instead of processing that node again. So this is an example of the commenting that we were talking about. So then we store that that 7 into the symbol table. So A will equal 7 in the symbol table. Continuing on, this second one will be similar. So 2 will be stored in 3, and then similarly, 2 will be stored in B with commenting from node 3. Then load A will take the value from the symbol table and put 7 into node 5, leaving that in the node value map. Similar for node 6, just takes the value of B from the symbol table. And then here for the add operation, we have 2 children nodes, but we notice that both of them are already in the node value map, so we don't have to process them again. We don't have to load A again or B. We just take it from the node value map. So we get 2 and 7 and add them, store that in this node for the node value map. So n7 equals 9. And then finally, we move to the last node. And again, similar thing. We see that node 7 is already in the node value map, and this is what's being returned. So we don't need to process it again, and it just takes it from the node value map and returns that as the end of the program. And then we're done. And so ideas for future work include extending the interpretation to more than one basic block of the IL tree. So we don't think that should be too big of an issue. A bigger one would be returning VP constraint as a result of the interpretation instead of the value. So I think the abstract interpretation will be really useful for the goals of this project, as opposed to the concrete values we currently support. Following up, we would like to have parameters for the methods that we analyze. Right now, we have hard-coded 2 and 7 into the values of A and B, for example, in the last program. So we would like to be able to pass variable parameters into these functions. And then finally, we would like to do more than just long operations. That's currently what we support, a subset of long operations. But we would, of course, would like to see integers, strings, bytes, and all that jazz. Any questions?
So what operators do you support right now? Is it just arithmetic operations
Yeah, so
on long data types?
yeah, so we support add, subtraction, shifting, load and store for long operations, and some conversion operations too into double. but definitely not all of them.
And is the expectation is that when you get to the end of these this chain of trees, that it's going to return a value, and that's the thing that gets stored in the compilation in some compilation object?
That's right. So from the sample program, if you call the interpret method from the JitBuilder, actually return the result of the interpretation.
Okay, so there are no other side effects. It has to reduce down to a single value that gets stored somewhere.
Yeah. So the interpretation result will be it's the same value type like struct that we have, or union. So it will be one of the supported data types.
Okay. So did you say that the way that you implemented this was as an optimization, and what you did was you created a special optimization strategy just for interpretation that includes just this optimization?
Yeah, so we created a tree interpreter optimization, which basically just has our tree interpreter and a end opt in it. And then as part of the interpretation, it exits the compiler early. And it stores the result as so as it goes through the compilation, that is the interpretation. And then it just exits early before returning an entry point into the method.
Okay.
We expect the result of the interpretation to always match what the actual execution of the IL would.
Yeah, Philip, the answer to that would be yes. You would expect that whatever the interpreter produced would match the result of running the compiled method.
Okay, so is one of the goals then to, I guess, generate IL that we can feed through both the interpreter and compiled body? I'm just trying to think of what the contrast is with our current trill tests. Would this augment them in some way?
So I think the reason for having an interpreter infrastructure would be to allow languages, well, in my mind, one of the nice things that we could do with a concrete interpreter would be to allow languages that hook up to JitBuilder to have the option to interpret as well as to compile, right? Because you may not want to invest in doing the full compilation. You may just want to have it and throw it away or whatever. And it would also allow verification of the code generators. If we have an interpreter that we believe is correct, then we could verify the code generators against the interpreter, and with the interpreter having its own tests. Now, the longer term goal is to have an abstract interpreter. So those of you who are not familiar with the open, or not doing a lot of work with the OpenJ9 compiler project, there's a research collaboration that we have, IBM has with the University of Alberta, where we have some researchers developing a new inliner optimization for the compiler, for the Java compiler. And that infrastructure is very powerful and largely language agnostic. However, it guides inlining based on abstract interpretation to try and figure out where optimizations might be exposed. And at present, there is no, because that abstract interpreter is on Java bytecode, it's not really compatible or runnable from OMR, right? It's an OpenJ9 thing. If we have this interpreter and we extend it to be able to support abstract interpretation and produce VP constraints, then we would be able to integrate that inliner into OMR, which would provide a much better inlining optimization than what we currently have.
That provides a lot of context.
So there's a pull request open for the code that Daniel and Alex have written. It's obviously still a prototype, but it's basically got the guts of what would be required to start flushing out the interpreter loop to be able to support the trees. And that's currently under review, so comments will be welcome on that.
Awesome. Thanks, Andrew, for stepping in and answering.
Any other questions for Daniel or Alex?
All right. I guess that's everything from us then.
Okay. All right. Thanks. Thanks, guys. Looks like a good start.
Yeah. Thank you for letting us work with you guys.
Yeah, thank you for the opportunity.
You're welcome. Okay. Let's see here. Okay. Next up, we have Robert Young is just going to talk about a proposal to rename some of the types. I guess it's primarily used in the GC and VM parts of OMR. I don't think we're going to be going through this in tremendous detail. I think that this is really just more for everyone's awareness that there is this proposal out there, and that you can certainly read through and join in the discussion that there is. But Rob is just going to be talking a little bit about what it is and what it's all about. So.
Yeah. So yeah, that's exactly right. I just wanted to bring this up so that people are aware, especially if you're working on some kind of project that's actually using the GC. This might affect you because it's a user-facing change. In the GC, we have a type called FOMR object T, and it represents an object-to-object pointer. So we use this all over the place for loading and storing pointers and objects, and for indexing into the fields of objects. But with the ongoing work to support runtime compressed references, it's no longer possible to map the size of an object-to-object reference with to statically map that to a C type. So what we're looking at doing is replacing or redefining this type from either originally it's a UINT32 or UINT64 depending on build, but we would redefine it to an incomplete struct, which would prevent users from indexing or doing pointer arithmetic or dereferencing an FOMR object T pointer. And so then you would be forced to go through some type of helper, which could make the decision either at runtime or at compile time as to how to actually load or index into a slot array. And yeah, that's it. So if you're using the GC, you may be, this is a glue type, so you would have your own definition. And I believe part of the proposal is to move the type from the glue code back into the GC, so it would be GC defined type. And that's it.
For the projects that that have integrated with the OMR GC, is there a lot of is the work that they would need to do obvious in order to keep their projects up to date with this change?
So it depends. What a lot of objects, what a lot of projects would probably do, and this is what we do in the example, is we define FOMR object T to be a different type. So in the example, it's defined to like a slot type. So as long as you're using your own internal types, and you're not using FOMR object T directly, it's possible that there are no code changes that you need to make. If you're interested in supporting runtime compressed references in your project, that is a much bigger that's a much bigger problem. You would have to basically change all the different ways that you're indexing into objects and reading and writing pointers. Yeah, for the majority of people, though, if you're happy with compile time compressed references, the answer would be just to replace this type with your own internal type.
Okay. Did you say that the I guess the example GC glue is going to be updated to show how one could take advantage of runtime compressed references?
Yeah, we're just starting to look at that now. Andrew is in the middle of a prototype. There are still changes that need to happen inside of OMR to support runtime compressed references. So the work isn't done yet. And it won't be possible to turn it on for a little bit, but it's getting there. And there is a PR open. It's linked to in the discussion.
Okay. Any discussion on this or questions for Rob? Okay, right. So I guess if you want to follow along there, it's 5027 is the issue. So you can keep yourself up to date with that. Okay, thanks, Rob.
Would this somehow map to the FJ9 object pointer in OpenJ9?
Yeah, I think the plan is to yeah, they are the same type. I'm actually not sure exactly how they're structured, which one is typed up to which. I think that the plan is that the same thing would extend to J9.
Okay. I think there's a bunch of uses of that in the compiler on the OpenJ9 side.
Yeah. So in some places, after we load a pointer, but we've for some reason chosen not to decode the pointer because we don't need to. One particular place is when you just need to tell if two pointers are equivalent without actually having to dereference either one of them. Sometimes we stack allocate FOMR objects, so those either have to be replaced with a runtime check. So you would say, okay, if I'm in compressed reference mode, load a uint32 and store that on the stack, or uint64. Alternatively, we are also talking about adding an OMR object token key. So that would be a token that you could decode into a pointer. And for whichever mode you're in, compressed, full, or mixed, it would be wide enough to store a pointer that has not yet been decoded. But it's kind of, we're not totally clear on whether a type like this would actually make sense, or if it's better just to sort of move the runtime check out to out a layer to the callers so that they can allocate the right type, like a compressed or uncompressed pointer.
Okay. Any more discussion on that? Okay, thanks, Rob. So next up, we have Ben Thomas is going to describe some of the work that he did in the past couple of months to add some means for testing the encoding that's coming out of the compiler. Oftentimes, it's not straightforward to validate all the different kinds of encodings and instructions, but there has been some work done recently in Power that just like to talk us through the methodology that he's using, because it could be useful in other backends as well. So Ben, you want to take it away?
All right, can you hear me?
Yes.
All right, excellent. So I don't have any slides here or anything, but first I just want to give a little bit of background on how this came up. Recently, there's been a lot of work I've been putting in to refactor a lot of the binary encoding on Power. And as even seasoned compiler developers sometimes take binary encoding for granted. We sort of just assume that it works. If we have a list of instructions, we sort of forget that there's the last step where they get encoded to machine code. And this can cause weird, hard to diagnose problems if it doesn't quite work correctly. This is compounded by the fact that we actually have a lot of instructions that are either not yet used, or they're only used in downstream projects like OpenJ9. So in OMR, there's previously been no testing of that at all. And these sort of bugs in that can sit around as sort of ticking time bombs that are waiting to go off and cause massive problems. So what I decided to do while I was doing the refactors is try to unit test this particular part of the compiler. And because of how functional this particular part of the compiler is in terms of it gets input and then it gives output and it doesn't have a ton of side effects, it's a really good candidate for unit testing. So what has to be done in order to set that up is actually a lot more complicated than it probably should be. Normally, when we initiate the compiler, we use a function called compile method from details. And that initializes all sorts of data structures in the compiler. And it also goes through the sequence of events that we usually want to do for the compilation. So IL gen, optimization, tree evaluation, peepholes, register allocation, binary encoding. That's a lot of stuff running there. And to isolate just the binary encoder, we need to feed it very particular instructions. So because of that, we can't use any of the existing infrastructure for starting and stopping a compilation. So instead, what has to be done is that we initialize a lot of the compiler data structures manually. This is a bit unfortunate, but it does work for the time being. And because of that, we have full control over the compiler when we have it in this state. So rather than having to give it trees at IL gen time, we can just feed it instructions directly to the code generator. And once we've done that, we can just call the generate binary encoding function on these instructions. And then we can run that on a fixed size buffer and just check the results. And that gives us a very powerful means of unit testing just this one particular part of the compiler. And it gives us a lot of control over what's going on in this test. So one big problem that you do run into when you try to do this is getting expected values. So the naive way would be to manually try to figure out, okay, I have this instruction, I want to figure out what the encoding should be. That's not really time efficient. So what I ended up doing on the power binary encoder is I actually ran the instructions I was going to encode through GCC as an assembly file, used objdump to dump the binary encoding of each of the individual instructions. And then I had a small Python script that would take that, clean it up a little bit, and throw it into a parameterized Google test. And by doing that, we can have one test fixture per type of instruction that we want to test. So for instance, one for instructions with a single target and a single source register, ones with a single target register and an immediate. So then what we do is we just use a Google test parameterized test, and we give it the opcode we want to test, any registers and immediates we want, and the expected result at the end. And it does the absolute bare minimum. It exercises as little of the compiler as possible to just focus on this one particular part. And that lets us have a lot more confidence in the results of this kind of test, because we know exactly which cases in the compiler it's exercising. And we know that it's exercising all of these instructions that we may not even be using yet, but that somebody may have the bright idea to use in the future, and may only be used in very specific cases that are actually really difficult to reproduce in a simple test case. So this has actually caught a number of bugs in the existing power binary encoder, where either our template instructions that we fill in fields of were wrong, or we just didn't fill in the fields correctly. So the basic test fixture that initializes and shuts down the compiler without using our normal infrastructure, that's actually not specific to these tests at all. It can be used on any of the code generators for any kind of code generator related test. So one thing I'd like to see is for some other architectures to try this as well and have their own unit tests for their binary encoders. And I'd like to see one particular part of the compiler here have a lot more confidence in its results than we have in the past.
So then I guess we're relying on GCC having, as the oracle, having the correct binary encoding.
Yes.
Right?
So that is a weakness, obviously, but the idea is that it'd be unlikely for us and GCC to make the same mistake.
And I guess you generated different arch levels with GCC to just capture instructions on different power processors. Is that correct?
Because I feed it in just assembler instructions, I don't have to do any funny business with architecture levels. I just set it to the maximum level.
Okay, but how did you generate the assembly instructions?
So generating the assembly instructions is a little bit harder. It's especially hard in the power code generator since we don't always agree with the ISA on how to specify things in an instruction. So a lot of the times we have multiple opcodes for the same instruction where the ISA would say that we should just have one instruction with an immediate. It's like 0 or 1. So what I did was I had a simple Python script. It was like 20 lines of mostly just print statements that would just loop through and print off the versions that we should use and the versions that should be fed to GCC.
So for the when you're actually generating the tests themselves, like the inputs to the tests, do you go through, like for a particular instruction, do you go through all possible registers that could be assigned to the target field?
That would be far too much. So mostly what I do is for registers, I would cycle through each register field, and everything except one register field would be register 0, and the one I'm testing would be register 31, so that the field would be fully filled with 1s rather than 0s. So unfortunately, it may miss something, but I try to tailor it to specifically how power encodes its instructions. So for instance, if we have certain immediates where they're divided between multiple fields, I'd try to use values that would exercise all possible cases. So it depends on the instruction.
Okay. And addressing modes as well?
Power doesn't really have those. That would be something that you would need to look into for other architectures, but with Power, each individual instruction has exactly one addressing mode, so it's not a problem here.
Okay. how much of the, if anything, of the infrastructure that you had to develop for this can be shared across the different architectures?
So everything regarding initialization and shutdown of the compiler without going through the regular architecture stuff, that can all be shared 100%, no problems. Most of the rest of it is a little bit power specific. So for instance, we assume that instructions are encoded as a series of words. So on other architectures, you would need to implement that yourself, because many architectures don't do that. Many architectures have a stream of bytes instead of a stream of words.
I suppose we can abstract that. x86.
Yeah, it's possible to abstract it, but I didn't go into it for this particular work.
Yeah, that's something that whoever does it next can do that.
Right.
Power is a special case here.
I mean, given the number of problems that you seem to have found with this approach, I think it certainly warrants an investigation on other architectures as well. I mean, there could be many problems lurking there that we just haven't discovered yet. So,
Ben, do you want to mention some of the stuff around memory references and displacements that we can't handle, and how that's handled with the unit testing?
Memory references are a bit strange because they work differently between different architectures. Specifically on power, it's memory references are either like a base register plus displacement or base register plus index register. And that displacement can have some weird stuff going on. We had some interesting behavior before where we would try to deal with out of range displacements. It was very unpleasant. That code used to live in the binary encoder, but I've actually moved it to run before the binary encoder now. So the binary encoder unit tests don't actually exercise that. That's exercised by a separate set of tests.
Okay, I see.
For the testing framework itself, how long does it take to actually run all the tests that you have? I mean, is this something that we would want to run, let's say, as part of a CI build, or is this something that we would just run?
Already hooked into CI. I think it's somewhere in like the 1-digit seconds that it takes right now.
Okay. It's relatively low impact.
Yeah, it's much lower impact than something like Trill because it doesn't initialize, bring up the whole compiler, only the parts that are absolutely necessary.
Okay. Well, I mean, I think that well, at least we can create some issues to at least get the investigation done on other platforms, and as resources are available or people are willing to put the time in, they can do this kind of investigation there. So, sounds very useful. Any other questions for Ben? No. Okay. Thanks for taking us through that and introducing that to everyone. I hope that we can find problems in other areas as well. So, okay, the next thing on our agenda is just a quick update to the JitBuilder 2.0 talk that Mark Studley made a couple of weeks back. I know he's made some updates to the repo, so I think he's on. There, Mark?
So I don't have a prepared update here, so forgive me if this is also in the same style of the presentation I gave before. Just kind of make it up as I go. Since the last talk, what I did was a bunch of cleanup, some modification, and there were some Slack conversations that happened after the architecture meeting last that it got some good feedback from people, and one in particular I managed to provide a rudimentary implementation for as part of the update that I've made. So I've now actually pushed a bunch of code to my own personal repo in the JB2 branch of mstudel OMR. And I guess I can talk a little bit about some of the things that I've added. So first off, it's still limited to basically implementing the operations and code needed in order to do a matrix multiply code sample. The reason why I'm not expanding it beyond matrix multiply right now is so that I can keep the set of operations low, and that means I can experiment with different ways of doing things and iterate reasonably quickly, just manually going through and modifying stuff without having to go and fix, another 100 operators or something like that. So I have the matrix multiply code sample using doubles, and there's also an example of the complex matrix multiply, which defines a new type called complex, which is a struct with two double values inside it, real and imaginary. And the matrix multiply JitBuilder code that you write is largely unchanged, and it just kind of works. Now, maybe I'll just share this screen and see what happens here. Oh, can I steal the screen, Daryl? Is that okay?
Yep, go for it.
All right, thank you. Okay, so this is my terminal. Hopefully you can all see.
Yep.
So the code right now is in the underneath the JitBuilder kind of main directory. There's a new directory called JBIL, JitBuilder IL. Which is a name that I created probably 8 months ago and haven't revisited. So anyway, it's just an old name. All of the code is sitting inside that directory, and then this is the code. This is kind of the base code implementation of JitBuilder 2, plus there's the matrix multiply code sample right there, matmult.cpp and matmult.hpp, which is largely speaking the unmodified matrix multiply code sample from that we know and quote unquote love from the JitBuilder code samples, the original JitBuilder code samples. And then there's also a directory here, complex matmult underneath, which looks like a complete second copy of this, but a lot of these are just symbolically linked back up into the previous directory. And then the mechanisms for doing this extension are a little bit interesting. So I've created yet another extensibility mechanism to handle this, but it's a lot simpler than any of the other ones that we have because it's largely speaking just a couple of classes. So I'll talk about that very briefly just so that it doesn't catch anybody by surprise. The two main classes in JitBuilder that I had to extend in order to create, or that I had to modify in order to add new operations and the new data type are builder and operation. So operation needs to have the three new operations called const, complex, conjugate, and magnitude. And builder, because you call in this world, you still call services, the operations on a builder object. Those operations have to be added into the API of builder. And so I did a very simple extension mechanism here, which is most of the implementation of builder is actually done in this file called builder base, very unimaginative name. I know some people have problems with the base, but anyway, that's what I started off with. So a lot of the implementation of builder from the JitBuilder perspective or JitBuilder 2 perspective is done inside this builder base class. And then there is actually a builder class that sits on top of it. And if we look at what's in builder.8, oops, I hadn't actually gone into the directory. Oh, it is there. It's actually very, very small, right? So it's designed for being extended by somebody, right? So it has designed integration points. If you have new public API, you put it here. you have to reproduce the, similarly to how our extensible class mechanisms works with the classes that are in the TR namespace, you need to redefine your constructors just because of the level of C++ that we're currently stuck with. And then, places to add various different kinds of facilities to the builder class. And because the whole rest of the code base refers to builder and not builder base, then anything that you add here just becomes part of the API that everyone's used to seeing. So it makes for a relatively easy way to extend things. And so if you look at, I'll just quickly, sorry, in the window, complex mult builder.hpp, you can see in here that I, added a new include to pick up my complex type dictionary. And then I added new operation services in here, the for complex, for magnitude, for conjugate, and that's almost all I needed. And I also added a way of getting a complex type dictionary, a typed complex. And then if you're in a builder object, you want to be able to work directly with the complex type the same way that you can work naturally with int 8, int 16, etc. In the original JitBuilder API, there's a complex type, which just basically caches what the type is that corresponds to this complex thing that's been defined. And then you can reference it very easily. So that kind of extension is very easy. It's a little bit more complicated in operation, but it's the same basic mechanism. And as it turns out, in the operation base is really only defining the operation class itself. In JitBuilder 2, there are actually subclasses of operation that are the ones that you actually use. So you create a subclass for every kind of operation. So for load, there's a class called load. There's a class called load at. There's a class called store. There's a class called add, etc. And those are all subclasses of operation base. Those are all actually implemented in the operation.hpp file. So they look like they're extensions, but really they're not. And then you can have similar kinds of extension point. You can just add your own new classes in operation.hpp. And the idea there is although my comment there is only one line, the idea is there to create enough of a tag that when you create a patch, it's very easy for any kind of merge process to automatically figure out where you've added your code to the base code that's there. And so even though it's not in a separate file, I think it should be fairly easy to auto merge, even if there are changes happening in the JitBuilder 2 implementation. So that's one thing that I wanted to talk about, because I did manage to make some progress on cleaning that up. It was a lot worse when I when I gave the first presentation on this, even though I didn't actually show what it looked like. So that's a little bit cleaner now, I would say. And then what else have I done? Let's see. So one of the things that came up in the Slack conversation was that it would be nice, Jan mentioned that it would be very nice to be able to attach source code locations to any of the code that you're working with. And although the OMR compiler tracks code locations very well using bytecode info and which has the call site and bytecode index associated with everything, there wasn't a very good connection to this, other than in the original JitBuilder API, there were bytecode builders, and each bytecode builder had a notion of a bytecode index that corresponded to it. And then any operations that you used in that bytecode builder would get tagged with the bytecode index of the bytecode builder. So I decided to generalize that a little bit and came up with the notion of a location, very unimaginatively named, which can be extended very easily. You can just add information to it the same way it would have worked in builder.hpp. But by default, it kind of creates automatically for you a bytecode index that can be used to correspond to an arbitrarily described source code location. So by default, you can do kind of 3 different ways of identifying a source code location. So these are just the ways that come with JitBuilder 2 right now. You can in a function builder, you can create a location that's based on just a string that's a line number or associated, like it could be a line number, it could be anything really. And another way is a line number and a specific bytecode index. So you could imagine this would get used later on by a real bytecode builder, would be creating locations this way by controlling what the bytecode index is. If you don't specify a bytecode index, then it just manufactures a bytecode index for you, just bumps a counter and gives the location a particular bytecode index. And that provides a mechanism to map locations that you're talking about in JitBuilder to with the bytecode index that will end up getting used in the OMR compiler. And the idea is that it doesn't do this now, but I imagine it would be not hard to implement some callbacks within the OMR compiler to map things back up into the source code locations of the function builder that's being compiled by looking up the location information or the bytecode index and getting the location information, and we could even incorporate that into some additional metadata that gets created for the code that you're building with JitBuilder 2. All right, so that's location. So that was a response to Dan's request. The other, what else did I do? The other thing that I did was to create this code generator thing, which is actually currently implemented as a transformer, even though it's not really a transformer. It's more of a visitor because it doesn't actually transform the code at all. But it basically uses JitBuilder 1 to generate code. So here's kind of where we let me get down. Here we go. So transform operation is something that gets called on every operation as it visits all the operations in the code. You basically just get the builder from the operation. You map that to a tr::il builder, which is the structure that you used in JitBuilder 1 when you were working with builders. It sets the bytecode index and makes sure that the OMR IL generator knows what the bytecode index is. So that's the location handling. And then just for every operation, it basically just maps. It takes the values that are coming from the operation and it maps those into tr::, whatever IL value, IL type, IL builders, and that's what some of these it's like store value does that, right? It looks up the tr::, IL value that corresponds to this result, and it creates a const int 8. Sorry, it calls const int 8 because this is a const int 8 operation on the literal value of that const int 8, so it's a byte, and it calls that on OMRB, which is the tr::il builder. So it's calling into the OMR compiler to create that tr::il value, and then basically store value just maps that tr::il value with the value that's here off of the operation. And then later on, you can see, let's pick something that actually takes an operation. Here you'll see it map operand value. So basically it's just looking up in that standard map, what's the tr::il value that corresponds to the operand value that's stored in the operation. And it does that for both the left and right operands. And then it does the mapping for the result. So it's actually, this was all the code that I had to write in order to map or to code generate for the JitBuilder 2. So now when you run matmult, which hopefully I have a current version of this that isn't broken compiled here, because I'm not in a state where I can recompile, it actually does at the end invoke the matmult compiled code and generates the result that it actually works, which was a nice thing. I actually discovered a couple of bugs when I did this, so it was good that I went through that exercise. I also discovered some things that made it work more efficiently as I was going through the process of trying to actually generate code. So right now, this is a very, I would call it brainless way of generating code for JitBuilder 2. I think we can actually do a much better job of this. I just wanted to get something working so that I could verify what it does. As you can see, it's tracking how much memory was allocated in the compilation of this function builder. So all of the memory that got allocated as part of the JitBuilder 2 operations that were done on this function builder are captured here. So it used a grand whopping 9K of data because it's not a very big function, pardon me. And this is kind of an example of some of the output. I can't remember if I showed this before in the in my talk last week, but basically, I think I did because I remember saying that square brackets are being used a lot rather than open parens because I didn't want it to look like Lisp. But anyway, I'll just go through it again quickly. So, this is a function builder with a name. It has a bunch of attributes that are described here. I use square brackets as just a way of delineating different pieces of data. So it's, I guess, a little bit XML-y, but not really. And so it just basically, it's easy to walk around in this file by choosing match. You can always find the matching bracket, and then it tries to do a little bit of indentation to make it easier to read. So as part of this function builder, when you enter this function builder, it will start executing this sequence of operations. It shows it's a redundant, but this is the builder object that owns this operation, and then it shows in a very sort of straightforward form. It's not using the tree form that I usually use when I'm writing JitBuilder code, or that the OMR compiler uses. But it's a very straightforward kind of statement style, explaining what it is that's doing and using values being defined on the left and can be used anywhere on the right, strings and so on. And you can have all kinds of different services. You can refer to builder objects. There's a little bit of syntactic pleasure there to help you understand which parts are which. And then, various different builders that are owned by this method builder will be listed as part of this function builder. And they show their code as well. They show whether or not they're bound and which operation they're bound to. So this builder B5, if we go back and look at B5, it's an append builder object from here. So this operation 40 did an append builder of B5, and that's why B5 is bound to that operation. It is a target of a branch, and it has a series of operations. And so this is just, you can go through the triply nested structure of matrix multiply and see all of the code that's in here. And you can read it fairly, you get used to reading it, I guess I'll say. Maybe it won't strike everyone as equally useful. Just as an interesting, this is the code generator that's going through here. You can cause the visit code to trace as it's visiting things, so you can see the order that it's doing things in. So this is just basically going through all of the operations in the code. And then an interesting thing I added, which wasn't done very well, I don't think, in the original JitBuilder debug output, is that it basically keeps track of the mapping that it uses in the code generator to map builder IDs in the JitBuilder 2 structures to the tr::IL builder pointers, the objects that are used in the compiler. So it just prints out those mappings so that if you do need to descend into what the OMR compiler is doing, having these pointers around makes it a little bit easier to sort of figure out where things ended up in the OMR compiler. I think this can be made a lot better, and I think a lot better collaboration between the OMR compiler and the JitBuilder 2 code can make this better. But for now, this is kind of the state of things. And then it gets invoked and run. There's one other thing I wanted to show you, which was for those of you who are familiar with the OMR compiler and the way that it has kind of a perform transformation facility that allows you to identify transformations, kind of calls out transformations that are being applied to the code base and what they do. So the model for transformer is basically you can visit operations, and as you look at that operation, if you want to replace that operation with some other code, you return a builder object that has whatever it is you want to replace that operation with, which is a nice generic kind of model. And then those operations, the builder basically evaporates, and those operations just get jammed into the spot where the original operation was. But it provides a nice model for kind of being able to describe at least most of what's being done inside of a transformation. And there is actually a perform transformation call that's made for any transformation that gets done by the transformer. And so that you can use, I guess, for any transformation you're going to do. And so this is an example of, this is the first transformation, so it's numbered 0. It shows the original operation that it's transforming. So in this case, it's going to translate this for loop into a lower level set of operations, so that for loop up no longer exists in the IL. And what it does is just replace this with the builder B4, which, as I said, is about to evaporate as it replaces it. And just these operations are going to be injected into the spot where the original op6 was. And so as you go through here, you can see there's another, it found another for loop up here. So this is transformation 1. And again, it prints out what that for loop operation looks like and what it got replaced by, and then so on. So, and there's transformation 2. So there's 3 for loops. So it replaced 3 for loops with basically the code to do a for loop. So it's a relatively nice model. Unfortunately, this printing capability only really prints the actual B12 operations. So if you, as part of doing this, and in fact, it actually happens in this transformation that's going on right now, if you create other builders like B13 that have other builders inside them that you've created as part of doing the transformation, it doesn't actually show those because it doesn't know how far down it needs to traverse. So it really only shows the top level builder that you created. But it's still a fairly good mechanism. And then this fact that they're numbered allows you to build some diagnostic facilities around, you know, disabling certain transformations to see if they're responsible for problems and so on. So it's kind of building in some of the similar diagnostic abilities that are there in the OMR compiler and bringing them into JitBuilder as kind of first-class citizens. And just to quickly make sure that I'm kept honest, this is the complex mat mult. So complex, I think I talked about this. There's a reducer transformer that basically goes through that process and replaces every complex operation with a pair of double operations in principle, and then does that same kind of mapping thing that I showed before to map one value to the complex value to the 2 parts of the double value, and then just goes through and transforms the code. You can run this, and so you can see it used more memory in this case because it had to create a lot more structures in order to do the transformation, and more builder objects got created and so on. But the outputs here, it printed out some nice, I didn't actually manage to put any imaginary values in here, so it's not a complete proof that it worked, but it did actually generate results. And you can kind of see in the, if I can go up to the transformer here that ran the reduction, which is here somewhere. Here we go. Just there's a couple of ones here that are an example here, right? So this add operation is an add that has these 2 operands are complex. So it maps V18 to a real and an imaginary part, and it maps to the real and imaginary parts of V19, does 2 adds, generates V83 and V84, which are both double results, and then it associates the real and imaginary parts of these values with V20, so that where it uses V20, now it's going to store into the real parts is the store of V20 is the sum of the dot product in the inner loop after finishing the inner loop. So V20 has a real and imaginary part, which we just created here, which are 83 and 84. And you can see that it just translated into 2 stores for V83 and V84. And then these, the sum variable also got blown apart into two independent variables that are used wherever you need to use sum. As you can see, there are 18 transformations applied as across this particular code gen.
So what's the benefit of doing this in JitBuilder versus just letting the OMR compiler do it?
Well, how would you do complex? Sorry, doing which part in JitBuilder versus doing it in OMR compiler? Introducing a new type called
store.
Complex, you mean?
No, that's store. I guess that's like copy propagation, effectively.
Which is, sorry?
The store example you just went through.
So it is copy propagation, but it's using a type that doesn't exist in the OMR compiler, right?
Oh, okay, I see.
There is no type called complex in the OMR compiler, so there's no primitive type called complex in the OMR compiler.
Right, but all of that would map to the base types, which are in the OMR compiler.
Correct. Yes, but there's no way to express it, I guess, very well in the OMR IL, compiler IL, without going through and doing all of the double translation yourself, right? If you look at what complex matmult.cpp looks like, the code for the guts of this thing are all the same. I didn't have to change anything to use doubles. The only thing I had to change was this one, the initialization of the sum variable to start with a complex type. Otherwise, it's the same. So complex is a bit of a simple example, but you could imagine blowing that up into, you could have types that are matrices or tensors, or they could be tables in SQL, right? They could be any kinds of things, as long as you know how to translate those representations of those things down into a lower level representation. You can write JitBuilder code that treats them just like a value, no matter what their underlying representation is. And then as long as you can translate the operations into simpler operations, you can kind of do that translation once, and then you can write a bunch of code that can work with those things as values.
Okay, I understand. Thanks.
So that's the idea. I admit complex is kind of a simple example, but it was the easiest one to kind of, since I was already working with matrix multiply, it seemed like the most obvious, easy thing to try. Anyway, so I guess that's kind of where I am now. Oh, I guess I'm in the middle of creating a binary representation for JitBuilder. It's kind of like the reader-writer code that we have in JitBuilder IL that isn't quite active right now, but it's the same basic idea. Starting to create this is leading me down kind of a slightly different notion of how to organize the various subclasses in operation and where things should reside. As an example, pretty printer that's here, this guy, which is the thing that prints out all of that wonderful text with all the square brackets. It's one piece of sort of encapsulated code that knows how to pretty print the JitBuilder IL, which means that it has all kinds of switches. Well, not all kinds. It has a big switch in it to deal with what specific operation you're dealing with, and then it knows what it has knowledge about how many operands and so forth and what their types are for those operations, which means that if you add a new operation, then you kind of have to go and update pretty printer with that data. I've kind of gone back and forth on this a little bit over the course of developing this, but I think it would be better if the actual subclasses had more information about how to do these kinds of things. So let me just give an example of just so you can see what they look like. So here's what an add operation is. There's actually a set of kind of helper classes that I built in the middle that help reduce the amount of boilerplate that you need to generate in order to define an operation. So any kind of binary operation that has two values, you can use this binary value operation. And then this is all the code that you have to write in order to provide a way to create them, define a constructor for creating them, and then if you want to restrict the types of values that are that can be used when you create an add, you can do this initialize type productions, which gets called with a type graph. So you can tell the type graph, I can only add int 8 with int 8, int 16 with int 16, int 32 with int 32, and you can't do crosswise things, those kinds of things. So it's just a way of doing that. So I think augmenting this with a few more things around some of the printing capabilities might be a better way to do that than collecting the sum total of everything in another class. But anyway, I'm still kind of experimenting with that and seeing what that looks like. In any case, I guess the main point that I wanted to finalize with here, I actually talked for a lot longer than I thought I was going to, is that the code I pushed to the repo is there. It's available on GitHub. You can go and look at it. There's a link. I basically sprayed links all over the places where we've talked about JitBuilder 2 before, Slack channels and in the JitBuilder 2 working proposal. And I'd love to get people's feedback. I know it only does matrix multiply right now, which is a fairly uninteresting thing, but anyway, I'd be happy if people would pick it up and play with it and give thoughts and ideas on it. And I guess I'll stop there.
Cool. All right. Thanks, Mark. Any more questions or discussion on that topic?
Are you considering, like I see you've got the reducers to reduce the complex type down. If you were to reduce it down and like not modify the tree, so you wanted to reduce it down to run some analysis that OMR supplies, would there be a way to the higher representation? Basically, like if you wanted to use use defs or liveness or something like that, could you map back up to save having to re-implement the infrastructure for every added type?
Yeah, I don't have a good story for that. That's an interesting idea. I hadn't really imagined that. Right now it works in kind of a one way. That's sort of the way it's imagined to work. But if you have thoughts on how that could work, I'd be interested to talk more about that. Because obviously it would be nice not to have to re-implement all of the infrastructure that we've got in the OMR compiler that could do things like use def and etc.
Well, yeah, and it's kind of one of the, well, if you look at the MLIR design and things like that, it's kind of one of the weaknesses of that design that the lowering is always monotonic, so you can't reuse. So it'd be nice to not have that limitation.
Yep, agreed. Yeah, it would be interesting to be able to whatever the reverse of collapse is, I guess, or the opposite of reduce. To come up with another verb that's the right verb for aggregating the information that you've learned at the lower level back up into the operations that did the reduction. That's interesting. I mean, let's think about that some more.
Yeah, or possibly if you could support that, then possibly even some of the, if you wanted to allow some classes of transformation, something more like the Roslin sort of notion of how to version IL or something could allow you to recover the original structures modulo the transform.
Yep. I was actually thinking about that when because we've had that discussion before. It was actually, I guess now that I think about it, we've had both discussions before. But anyway, I was actually thinking about specifically about the Roslin notion of this kind of immutable. Like you can create new IL without necessarily losing the old version of it. When I was doing that transformer code, and I ultimately ended up like just kind of cutting off that line of thought just to make progress on it. But it seemed to me that the model of taking an operation and replacing it with a builder object and having that be the consistent model for how the transformers work gives you a touch point to be able to control that and potentially build on that as to build up that sort of version notion of IL. But my brain started hurting as I thought more about it, so I stopped and cut it off and just implemented it as a straight replacement. But I think that's the integration point where you start thinking more about that.
One other question related to your source line information or your location notion. Are you given any thought to character ranges? Like, I mean, things like Clang and some of the LLVM infrastructure are famous for, being able to highlight particular ranges of code in a line and all that kind of stuff. Do you think that would scale onto the bytecode mapping that you have, or do you think that there would need to be another iteration on that to support it?
Well, so I mean, in principle, you could define like you could just add character start and end indices into the location structure that's there right now. The main question, I think, would be whether you'd run out of, depending on how many, it kind of depends on how big a function builder you're going to create, because that's kind of the level at which you'd reuse bytecode indices right now. So whether you'd run out of bytecode indices, I think we're at 16, it's a 16-bit int for bytecode index, if I'm not mistaken, in the bytecode info. Or did that get blown up to 32 bits at one point?
No, it's 16 bits, but it's signed, so 15 bits is usable.
Yeah, okay. So that's 32,000 different source code locations. So as long as you didn't blow that budget, then I think it would work as is. I think if not, then we'd have to come up with some other mechanism for dealing with that. Right. Because I mean, in principle, a bytecode index is just a name for just a number that corresponds to some source code location. Really, the fact that it's called bytecode index is just because of how it was originally devised. But we use it as just kind of a source code location proxy, right? Does that answer your question?
It does. I think I don't know what level Jan was interested in, but it may bear a little bit more thought, just because to have a really rich experience like the more modern languages can provide you, having that level of detail is something that people are pretty interested in.
Yeah, okay, fair enough. It's a fair observation.
All right. Well, if there's no other questions, thanks very much, Mark, for taking us through that and showing us in real time what that looks like. That was our last topic for this week. So we will adjourn and convene again in 2 weeks. Thanks, everyone, for joining. Bye.
Thanks. Bye.